All right, and welcome back, everybody. This is part 2 of our autonomous ODEs and population dynamics series. We've finished last time by giving two basic models for population growth, and the second of which, right? So first we talked about Malthusian growth, which is effectively just constant per capita growth, but we also employed and constructed and employed a model for what happens when you penalize large population sizes, right? And this is what we came up with in the logistic growth model. So we came up with this fellow down here, right? And we went through how to actually solve that explicitly. There was an explicit solution. We looked at what the graph of these solutions looked like, that eventually populations want to go toward the carrying capacity, but no further beyond. And that's a phenomenon that we'd actually like to explain without having to go through solving the differential equation explicitly. So let me give you an easier way to think about this, or a very particular way to think about this. And this is specifically for autonomous differential equations. Let's begin with the idea, or not the idea, with our example. We'll go through an example. We are looking at the logistic curve, or the logistic model, and that was ry 1 minus y over k. Right, r was the intrinsic growth, and k is the carrying capacity. And eventually we're going to put an initial condition in here at some point. But for right now, let's focus on this guy. This, on the right-hand side, this is our growth function, our rate function. This is dictating how quickly our population grows or decays. But let's actually think about this in a different light. What if, bear with me here, it's going to sound a little strange to do this on the outset. What if we graphed what the derivative dy dt looked like as a function of y? Right, and this would just affect, if we were writing this in y and x notation, we're just literally graphing using standard Cartesian coordinates. We're graphing what this function looks like, right? And this would be on standard y versus x axes. So first, let's remember that we're dealing with a physical problem. So there's context here. If we're dealing with population growth, there's very little to be gained by looking at negative population sizes. So we are going to highlight our exclusion zone, right? There should be nothing to the left here, right? If y is less than 0, the problem is non-physical, okay? So that leaves us with graphing what this looks like, what our curve looks like, our rate function. And this, you'll notice, is a parabola. This is a downward-facing parabola with roots where either ry is equal to 0 or 1 minus y over k is equal to 0. So that would be here at 0 or at k. So let me go ahead and mark those. Okay, so this already shows us that our derivative is 0 whenever y is equal to 0 or y is equal to k. Right, so that, because there's no dependence on time here, that means that once we hit 0 or once we hit k for a population size, then our population does not grow or die. It just stays fixed. So let me go ahead and put this back in white. Y equals 0, and I'll say y of t, just to emphasize it's not just a number, this is an actual function. Y of t and y equals 0 and y of t equals k are what are called equilibrium solutions. Right, and this is just to emphasize that once we hit these values, there's no more net exchange. Right, you're either growing or dying or some combination thereof, and the equilibrium solutions have balanced those so that there is no net change in the population size. That is not to say that individuals are not being born or that individuals are not dying in the population. It's just that those two quantities are balanced. Right, the number of individuals dying in the population is being replenished by the number of individuals being born into the population. So let's continue. What does the rest of this parabola look like? Well, it's an upside down parabola passing through these two roots. And to the left, nothing makes sense, but to the right, I get a parabola. And this guy continues down to minus infinity. Wonderful. So let's think about what this means for our population. If we're looking between y equals 0 and y equals k, then my curve, my blue parabola here, lives above the y-axis. And the y-axis here, or the vertical axis, I should be very careful here. The vertical axis is telling me about the slope, not of this blue curve, right? So it's the slope of a function, but not of the blue curve. But it is telling me that the slope of my y, right? So y prime is greater than 0 between 0 and k, and y prime is going to be less than 0 after k, and technically before 0, but we're not including those values because they're non-physical. So the point is that my solution, because it has a positive slope between 0 and k, my solution must be increasing in between 0 and k. So if I were to plot this, that means that y has to be increasing between 0 and k. And very similarly, because I have a negative slope down here for y greater than k, I know that my solution has to be decreasing when y is greater than k. And we saw this last time. If I go fish out those notes, we were looking at autonomous ODE, right? If I fish that out from last time, we saw this, right? Between 0 and k, y is increasing. I have a positive slope there. And when y is greater than k, my solution is decreasing. And very, very technically, I would also have a downward arrow out here for solutions that are exponentially decreasing for y less than 0. But we're not including that case. So if we go back to the new note, this is exactly what we see in this, right? And I didn't have to solve the equation in order to know that's what was happening. So that means that I can tell you even more, that I know that solutions want to travel toward k when they are near k, and that they want to stay away from 0 whenever possible. So that would mean that k is what we call, so y of t equals k. This is or actually, let me go ahead and make sure we make the distinction now. Y equals k, the number, this is called a fixed point. And actually, both of these, let me say y equals k is a stable fixed point. Y equals k is a stable fixed point. Right, so the value, right, that value y equals k, that is a point that we can substitute into the rate function to figure out that nothing is moving. The solution, y of t equals k, is an equilibrium solution, right? So a function is an equilibrium, or an equilibrium is a function, and a fixed point is a number. And very similarly here, y equals 0 is an unstable fixed point because solutions want to go away from 0 when they're nearby, right? And the way to read this, we would have some initial condition, right? Y of 0 would live somewhere on the y-axis here, right? You're thinking about these as parametrized curves living on the y-axis. And we're just asking, what happens if you drop your initial condition at this red location? Well, the yellow arrow says that it wants to move to the right toward k. So if I were to plot that, then I would see, let me see if I can remake that diagram. Here's the k, and here's the 0. And I would say y versus t would be my solution types here, or my solution functions. That means that I'm starting near 0 and then going toward k, where my slope, right, the largest increase occurs in between 0 and k. So that means that my slope is very, very steep in the middle, but much, much shallower near the equilibrium or near the fixed points. So that's how I know that this guy has kind of a sigmoid shape, that it has to have some sort of point of inflection in the middle here. And if I start my initial condition up higher, right, that would be up here, then my solution would want to flow toward K. And that's how I know I have this decaying exponential up above, right? And I can still create the same plot that I had before on the other video, but just by knowing that, or just by knowing how the rate function moved or how the rate function behaved. So again, I didn't have to use an explicit solution, which I may or may not actually know what it looks like, in order to solve for the eventual behavior of this system. And we can actually try to do this for a more general class of functions. So, or another growth model. So as another example, what we wind up with in this case, we want to model logistic growth. So we want a population that grows via logistic growth, but we also want to include something about genetic diversity. We want their, actually, so let me make sure I set this up correctly. Populations that exhibit genetic diversity are usually just diploid organisms, right? Where if you don't have enough genetic diversity, then there's not enough mixing of antibodies and successful genes for your population to sustain itself, to effectively outwit nature and to adapt to it. So we'd like to employ a third rule that the population dies out if it is too small, right? If we don't have enough genetic diversity in that population, that usually means that there's not enough individuals in that population to create genetic diversity. So we're adding one more term here, and we have logistic growth, 1 minus y over k. But we also have to add one more term in here, and I'm going to call it a threshold, so call it y over a minus 1. Okay, and why is it y over a minus 1? Because I need this guy to be negative if y is small, right? So if y is less than a, then y prime would be negative. If y is greater than a, then y prime is positive. And this was what matches our intuition for this third rule. So specifically, a and k need to be in the relative sizes here. A is going to be usually a very small number, and k is going to be a relatively large number. So we usually indicate that by giving double inequalities here. A is much smaller than k, is how that is read. And when we do this, let's employ what we just learned. Let's create dy dt versus y-axes. This is something called a phase diagram, and we're going to go ahead and use it. Remember, if y is less than 0, we have non-physical results, so we're going to leave that alone. And then we ask ourselves, what does this rate function look like? Well, it's now a cubic curve instead of a quadratic curve. And this is that'll be a plus y, a minus y, and then another plus y. So it is a negative cubic, which means it starts high, goes through 0, definitely going to go through k later on, but it also has to go through a new parameter, which means it has to scoop back up and then eventually fall back through k. And we go ahead and make the remark that, yes, whenever the blue curve is above y, y prime is positive, which means that my solutions want to increase. If I'm below the y-axis, solutions have a negative slope and want to decrease. And this is exactly what we're looking for, that there is this threshold up here at a below which our population dies out, and above which our population grows toward K, grows or dies toward K. And our solutions would then follow the following diagram here, where we have a K upstairs again, but now we have an A down here, so K, A, and then 0. So solutions will flow away from A and either toward A or toward 0 or toward K. And this is a complete diagram of what solutions do. And I didn't have to solve a damn thing. So there you have it. There is another way for you to solve a differential equation without actually solving it, without actually finding an explicit solution. So there is a place for graphical solutions. And for more on this, I actually have a playlist on dynamical systems, which you are more than welcome to peruse at your leisure. And we talk about exactly those kinds of equations, where we deal with first-order systems of autonomous differential equations. So it's a class in smooth dynamical systems. But I digress. This is a very basic outline of how we can study certain contexts, certain physical problems. That there is a natural progression from a hypothesis to a differential equation to a solution, and then out to intuition and understanding. And I think all three of these books, right, these references, these are standard in the field of mathematical biology, and I highly recommend, if you are at all interested in what we were just talking about in the past two videos, if you are at all interested in population or ecology, population dynamics, ecology, or just mathematical biology in general, I highly recommend checking out any one of these three books. They're very, very good, and they are, in fact, industry standards at this point. A staple on anyone's bookshelf. So let's go ahead and kill the video here, and I think you can see at the bottom of the page, this is where we're going next, right? We've